Today we're going to talk about infinite series. So remember, a series is the sum of the terms of a sequence. An infinite series would be a series that has an infinite number of terms. So you'll have some starting value, and then your ending value is infinite. Okay. So the first thing we're going to look at are partial sums. So the notation for partial sums is Sn, is called the nth partial sum of the series. If the sequence of the partial sums has a limit, then the series is said to converge, and S, the sum, is the sum of the series. If the partial sums diverge, then the series is said to diverge. So convergent and divergent series. So let's look at the series from 1 to infinity of 1 over k times k plus 1. So let's look at the first 6 terms. So remember, you start with this. So we're going to have 1 over 1 times 2, which is going to be 1/2. We're going to have 1 over 2 times 3. So you just go up by integer values. So that's 1/6. 1 over 3 times 4 is 1/12. 1 over 4 times 5 is 1/20th. And then 1 over 5 times 6, no, that's only 5, is 1 over 30, and one more. 6 times 7 is 1 over 42. Okay, now we're going to write the first 5 partial sums. So I'm going to do this in a chart just to organize it. So I'm going to have n, Sn. So n is going to be 1, 2, 3, 4, and 5. So the sum of the first 1 terms is just going to be 1/2. The sum of the first 2 terms is going to be 1/2 plus 1/6. So that would be, this would be 3/6 plus 1/6 is 4/6, or 2/3. Okay, the sum of the first 3 would be 1/2 plus 1/6 plus 1/12, but we already know what the first 2 add up to be. So I'm going to have 2/3, and I'm going to add 1/12 to that. So this will be 8/12 plus 1/12 is 9/12, which is 3 over 4. And you may start to see a pattern appearing here. 4 is going to be 3/4 plus the next term, so plus the 120. So multiply this by 5 over 5, we get 15/16 plus 1. So we get 16/20, which is 4 over 5. Last one here, we're going to add the 4 over 5 plus 1 over 30. So we're going to have 24/30 plus 1/30 is 25/30, which reduces to 5 over 6. So if we look at our final numbers here, 1/2, 2/3, 3/4, 4/5, 5/6, there's a clear pattern. So we can come up with the formula. The top number is always going to be the number of terms we're adding. So that's going to be n, which makes the denominator n plus 1. Okay. So does it seem to converge? Yeah, this number is always going to be 1 bigger than 1. So essentially this is going to go to 1. This is going to be, you're going to have 99 over 100. You're going to have 999,000 over 10,000. So yes, it does seem to be converging because it's never going to be bigger than 1. So if the partial sums converge, the series converges. S is the sum. So this one's sum is 1. This, as we continue to add more and more and more and more terms, the sum itself is 1. Okay. So using partial sums, find U50. So we want to find the 50th term. If I'm using partial sums, that means I'm going to take the sum at 50 and subtract the sum at 49, because what that's going to leave me with is just the 50th term. Well, using our formula that we came up with, that'll be 50 over 51 minus 49 over 50. You get a common denominator, which you're probably going to need a calculator for anyway. You end up getting 1 over 2550 as the 50th term. Okay, is this the same as evaluating u of k at k of 50? So going back to our original 1 over, so this would be 1 over 50 times 51, which is still 1 over 2,550. Okay, so we have this series from 1 to 100 of -1 to the n plus 1. So we're going to find the first 6 terms of the series. So when I plug in 1, we're going to have a -1 squared, so that's going to be 1. If I plug in a 2, that's now cubic, which is going to make that a -1. Then we're going to go to an even, then another odd, then another even, then another odd. So the series is just going to alternate between positive and -1. Okay, so let's make a chart for our partial sums. So the first one is 1. Then I'm going to add 1 and -1 to get 0. Then we add a 1 to get 1, then a -1, back to 0, and so on. Okay, so my formula here, I'm not going to write out necessarily a formula, but I'm just going to say the sum is 1 when n is odd, and the sum is 0 when n is even. Okay, for a sequence to converge, it has to go to a single value, and this is not going to a single value. So this is not an infinite, or this is not a convergent series because it keeps bouncing around. Okay, determine the first 4 partial sums, and from that we'll see if we can find a pattern and determine if it converges or not. So let's go ahead and write out the terms here. So starting at 1, we're going to have 2 to the 0, which is 1 over 4. Plug in 2. We're going to have 2 over 4. Plug in 3. We're going to have 4 over 4. And then 8 over 4. Okay, so we'll add those and see if we see a pattern. So we're going to have 1/4. Then I'm going to have 1/4 plus 2/4, so 3/4. Add on a 4/4 would make this 7/4. And then 15/4. So the numerators here are getting bigger. The denominators are staying the same. So this is just going to keep getting bigger and bigger and bigger. So this series does not converge, it diverges. Okay, now we're going to look at some other types of series. This series here is what we call a telescoping series, and you're going to see why. Okay, so I'm going to start by plugging in 2. So I'm going to have 1 over 2 minus 1 over 2 minus 1, or 1. That's my first term. My next term, I'm going to plug in 3. So we're going to have 1 over 3 minus 1 over 2. We're going to have 1 over 4 minus 1 over 3. Let's do one more. 1 over 5 minus 1 over 4. Okay, so this is going to continue infinitely, and we're adding. So if I look here, I've got a 1/2, and then I'm subtracting 1/2. I've got a 1/3 and I'm subtracting a 1/3. I've got a 1/4 and I'm going to subtract a 1/4. I don't have the next term here, but it's going to have a 1/5 that we're subtracting. And that's going to continue infinitely. So what we're left with is just that guy. So this adds up to -1. Okay, our next one here. Can make this k minus 1 and k plus 1. And then we can use partial fractions to separate them out into something that looks like this one. We're going to have 1 over k minus 1, k plus 1 is going to equal a over k minus 1 plus b over k plus 1. So 1 is going to equal a times k plus 1 plus b times k minus 1. So we're going to pick convenient values of k, starting with -1. So that'll make that go away. So we're going to have b times -1 minus 1 is going to be -2. So my b is going to be a -1/2. Then for my next one, we'll pick 1. So when k equals 1, we have 1 equals a times 1 plus 1, which is 2. So a is 1/2. So I'm going to go back up to my problem here. This is now going to be a was 1/2, so 1/2 over k minus 1 plus -1/2 over k plus 1. So I'm going to pull out a positive 1/2 here. And that's going to leave me with 1 over k minus 1 minus 1 over k plus 1. And then evaluate. So we're going to plug in our values starting at 2. So we're going to have 1/2 times, if I plug in 2, I'm going to have 1 over 1 minus 1 over 3. Plug in 3. We're going to have 1 over 2 minus 1 over 4. Plug in 5. Sorry, plug in 2, 3, 4. 1 over 3 plus 1 over 5. Go ahead and do one more here. 2, 3, 4. Now we're plugging in 5. So 1 over 4 minus 1 over 6. And so on. Dot, dot, dot. This 1/3 will cancel with this 1/3. This 1/4 cancels with this 1/4. We didn't draw it, but there'll be a 1/5 out here somewhere. There'll be a 1/6 out here. So we're left with a 1/2. And then my series is now just 1 plus 1/2. So we get a sum of 3/4, and this again is convergent. All right, infinite geometric series. So an infinite geometric series has a common ratio. And we did this in pre-calculus. Okay, if the common ratio, which is r, is between -1 and 1, we can find the sum of the series. the series from 0 to infinity of a1 r to the n. So if I plug in a 0 here, that goes away. So my first term is a1. And then we're multiplying by r over and over and over again. The sum is a1 over 1 minus r. Okay, so we can find the sum of an infinite geometric series using this formula as long as r is between -1 and 1. So it's been a little bit, so it may be helpful to expand out the series first. So starting with 1, my first term here is going to be 1/5. If we plug in a 2, we're going to have 1/25. We're going to plug in 3, we get 1/25, and so on. So this is an infinite geometric series with the common ratio of 1/5, which is between -1 and 1. Our a1 is 1/5, and then we just simply plug it into a1 over 1 minus r. So a1 is 1/5 over 1 minus 1/5. So that's 1/5 over 4/5, or 1/4. Okay, so this does converge, and it converges to 1/4. Okay, we'll do that again with e over pi. So plugging in 1, that's going to be 0, because we're going to have, raising it to the 0, so we're going to have 1, plus e over pi, plus e over pi squared. Okay, well our common ratio here is e over pi. So is that between -1 and 1? Yeah, e is about 2.718, pi is 3.14. So that works. My a1 is 1. So the sum is going to be 1 over 1 minus e over pi, which can simplify. You can get a common denominator and everything, or just leave it like that. Okay. Next one, or really next two, they look pretty similar, right? This one, plug in 0, that becomes 1, so we just have 2. When we plug in 1, we're going to have 2 times 3/5, which is 6/5. Plug in 2, we're going to have 9 times 2, 18/25, and so on. So this one has a common ratio of 3/5, and it's always going to be this value if it's in this format. So that is between -1 and 1. So my sum is going to be 2 over 1 minus 3/5. So that's going to be 2 over 2/5, which is, copy dot flip, 10 halves, or 5. The next one here, my common ratio is going to be 5/3, which is bigger than 1. So this one's going to diverge. Next one, again, we'll write out some terms. So if I plug in a 0, we're going to have 2 times 3 to the 1. So we're going to have a 6 over 5 to the 0, which is 1. Plug in a 1, we're going to have 2 times 9, which is going to be 18 over 5. Next one's going to give us 54, because it's going to be 27 times 2, 25, and so on. So my common ratio is, again, 3 over 5. We're multiplying by 3 across the top, 5 across the bottom. Okay, so that is between -1 and 1. My a1, though, here is a little bit different. So the sum is going to be 6 over 1 minus 3/5 be 6 over 2 fifths, which will be 30 over 2, which is 15. Okay, our next one here, the series is already written out for us. So we're multiplying by 3 on the top, 4 on the bottom, and if you notice the terms are alternating, so my r is going to be a negative 3/4. So my sum is going to be 3/4 over 1 minus a negative 3/4, or plus 3/4, which will be 7 over 4, which is 3/7. Okay, this one looks complicated, but it really isn't, because sine of pi over 3 from our unit circle is just the y value of pi over 3, which is root 3 over 2 to the n. So this is a series. If I were to write it out, I plug in a 0, I'm going to get 1. My next one would be root 3 over 2. Next one would be root 3 over 2 squared, and so on. So my a1 is 1, and my r is root 3 over 2. So my sum would be 1 over 1 minus root 3 over 2, which is that guy. Okay, we've got cosine squared to the k. So if I were to write this series out, starting at 0, we'll have 1. Then we're going to have cosine squared to the first power, cosine squared squared, and so on. So this is a geometric series. My a1 is 1 over 1 minus cosine squared, because that's my common ratio. And then we're just going to plug in 1. So f of 1 is going to be 1 over 1 minus cosine squared 1. When you enter cosine of squared 1 in your calculator, you need to do cosine of 1, take that value and square it. Or put it in parentheses. But we're going to get 1.412. Alright, this one, we got a lot of moving parts here, so we're just going to start plugging in values starting at 1. Okay, so if I plug in 1, this will be positive. This will be, I'm just going to write out 7 cubed over 4 to the 0, which is 1. Plus, when I put a 2 in here, that's going to be negative. So we're going to have a negative 7 to the 4th over 4 plus 7 to the 5th over 4 squared, or 16. So this one has an a1 of 21, and what's our common ratio? Negative 7/4. Okay, which is not between negative 1 and 1. So this diverges. Okay, what that doesn't mean, you can plug this number into a1 over 1 minus r. It's just that number is meaningless because this series gets bigger and bigger. All right, throw some integrals at you. Okay, so I'm going to integrate this. So we're going to have 3t plus a 9t squared plus that divided by 3 is 27t cubed. This divided by 4 is 81t to the 4. We're evaluating this from 0 to x. So if we plug in x, we're going to have 3x plus 9x squared plus 27x cubed plus 81x to the 4th, and so on, minus 0. Okay. So this is a series, and we're going to do power series here shortly. a1 is 3x. My common ratio is also 3x. So this series is going to equal 3x over 1 minus 3x as long as the common ratio is between -1 and 1. So as long as 3x is in between -1 and 1, then this is the sum of this series. Okay, so we're going to express 2.323232, a repeating fraction, or a repeating decimal as a fraction. So it's going to be 2 plus 0.32 plus 0.0032 plus 0.00032, and so on. So this is 2 plus 32 hundredths plus 32 10 thousandths, and so on. So this is a geometric series. Well, this part, the 2 doesn't get included. So this will be 2 plus A1, which is 32, over 1 minus R, which is 1/100th. So we're going to have 2 plus 32 hundredths over 99 hundredths. So we're going to have 2 plus 32 over 99, which you can multiply this by 99 over 99 and add it, but we're going to get 230 over 99. Okay, our last problem here, a ball is dropped from a height of 8 meters. Each time it strikes the ground, it bounces vertically to a height that is 2/3 of the previous height. Find the total distance traveled by the ball. So this ball is going to drop 8 feet, 8 meters. Then it's going to hit the ground and bounce up 2/3 of that, which I'm just going to say 8 times 2/3. It's then going to fall that same distance. Then it's going to bounce back up 8 times 2/3 times another 2/3. And I'll do one more down. So this one is sort of a geometric series with an A1 of, we'll talk about A1 in a second, with a common ratio of 2/3. But we're multiplying by 2/3 here and not here, 2/3 here and not here. So I'm repeating these ones. So I'm going to group these and then just add on the 8 because that's the only one that's not going to get repeated. So I'm going to have 8 plus 2 times the infinite series representing all of this. So the infinite series here is going to be A1, which is 8 to the 2/3, over 1 minus R, which is 2/3. So this would be half of them, and then we double it to get all the ups and downs. And you can do all this math, but it ends up being 40 meters. So infinite geometric series are an important tool in convergence and divergence and finding sums.